Good afternoon, everyone. I am Mojinto Mondol. I am going to present my work on ECG quality detection and noise classification for wearable cardiac health monitoring devices in the 16th edition of International Conference on Electronics, Computers, and Artificial Intelligence. The outline of my work includes introduction, literature review, major objective, proposed method, results and discussion, conclusion, acknowledgement, and finally references. ECG signals represents the electrical activity of the heart, which can be recorded non-invasively and are analyzed for cardiovascular disease detection and monitor vital signs. These ECG signals can be recorded continuously by wearable devices. While recording continuously, the ECG signals are contaminated with noises like electrode movement, muscle artifacts, random noise shown in Figure 1A, B, C, D, and respectively. Figure 1A represents a clean ECG signal. So the analysis of these noisy signals generates false alarms, and the device misdiagnoses the disease, and the reliability of the device reduces. So, to improve the reliability of wearable cardiac health monitoring devices and to reduce false alarms, we need ECG quality detection method, which can detect clean and noisy ECG signals and remove noisy ECG signals from further analysis. And ECG noise classification method classifies the noise type of noise present in the ECG signal, and accordingly noise specific denoising technique is implemented on the noisy ECG signals. So this can reduce false alarm rate. Noisier ECG data transmission for remote health monitoring can reduce the data transmission cost. From the existing literature, we get to know that ensemble empirical mode decomposition decision rule based method for ECG noise detection and classification, convolution neural network based ECG quality detection, a multi-stage decision tree algorithm for detection and classification of ECG noise decomposition, signal decomposition on a mixed code book based ECG noise detection and classification method, derivative ECG based CNN, and moving average derivative filter and temporal feature based classification of noisy ECG signals, spectrogram based CNN for ECG quality assessment, and recurrent neural network based deep learning and CNN based deep learning method for ECG noise classification. But the existing literature have the limitation that a few of them have not detected or classified the type of noises present in the ECG signal. The feasibility and resource constant platform of the existing methods is not evaluated. The processing time for noise detection and ECG quality assessment is not computed. So the major objective of our work includes the development of lightweight and resource efficient ECG quality detection and noise classification method, develop a robust method to achieve high ECG quality detection and noise classification performance with unseen ECG data, implement on Raspberry Pi to test the feasibility of the method on a computing platform with limited computing capacity, compute processing time for quality detection and noise classification of 5-second ECG signals on Raspberry Pi computing platform. Here we present the block diagram of our proposed method, which includes database creation, hyperparameter tuning of CNN models, and implement the base model on Raspberry Pi computing platform. So the database creation includes training database, test database. The training database is created by from MIT-BH arrhythmia database and PTB database. We have 4 classes of signals of ECG signals: the clean ECG, ECG with muscle artifacts, ECG with random noise, and ECG with electrode movements. So with the training database, we train the CNN models which have convolution layers, match pooling layers, flatten layer, and dense layer. So the in hyperparameter tuning, we have changed the number of convolution layers, number of dense layers, and the activation function in the convolution layer and dense layer, and also we have trained the model for different kernel sizes in the convolution layer. So here in table 1 we have shown the database that we have considered: the MIT-BH arrhythmia, which is a 2-lead database, and a PTB database, which is a 15-lead database. We have considered the ML2 modified lead 2 of MIT-BH arrhythmia and all the 15 leads of the PTB database for training the model to include all morphological features from different ECG leads. And while testing, we have considered the Fusionet Cardiologic Challenge 2011 database, which is a 12-free database, and the total training data is of 147087 segments, and the test data is 30430 segments, and each segment is of duration 5 seconds with a sampling frequency of 360 Hz. For hyperparameter tuning, we have considered 2, 3, and 4 convolution layers. And the kernel size we have considered is 3x1, 4x1, and 5x1. And the activation function in the convolution layer and dense layer are ReLU and ALU with softmax activation function in the output layer. And the number of dense layer are 3 and 4 3 and 4, and the sparse categorical cross entropy loss function is considered while training with and the learning rate is set to 0.001 with adaptive moment estimation and optimizer for training the CNN. The CNNs are trained with a batch size of 10 and for 100 epochs. Table 3 presents the performance, the accuracy of the proposed method for ReLU based and ALU based models for different kernel sizes, and the model architectures of 2 convolution layer, 3 dense layer, 3 convolution layer, 3 dense layers, 3 convolution layers, and 4 dense layers, and 4 convolution and 4 dense layer. We can see that the model with ALU activation function, kernel size 4x1, 2 convolution layer, and 3 dense layer, with 8 kernels in the first convolution layer, 16 kernels in the second convolution layer, and 16 neurons in the first dense layer, and 8 neurons in the second dense layer, and the 4 neurons in the output layer has the highest accuracy with 94.87, and it has a model size of 1409 KB. Here we present the convolution matrix for different kernel size for the ALU based CNN models, and we see that the model with kernel size 4x1, 2 convolution layer and 3 dense layer has the least misclassification of clean ECG signals of 16.09, and the other noise ECG signals, like the ECG signals with electric movement, muscle artifacts, and random noise are correctly classified from the range of 98.56 to 99.90. For ALU based CNN models with kernel size 3x1, 4x1, and 5x1, we see that the model with kernel size 4x1, as shown in figure in convolution matrix B, has the least clean ECG signal misclassification rate of 7.81%, and from among, if you compare the performance of ALU and ReLU based activation function based models, we see that the ALU based activation function model with kernel size 4x1, 2 convolution layer and 3 dense layer has performed the best among all the models. The testing time for quality detection is 0.256 for a 5-second ECG signal for the based model with ALU based CNN. Here from the plot 5, from the figure 5, we see that the x-axis represents the architecture of the CNN with 2 convolution layer, 3 dense layer, then the 3 convolution and 3 dense layer. We see that with the increase in the convolution layer from 2 to 3, the processing time increased, while with the increase in the dense layer, like in 3x3 and 3 convolution layer, 3 dense layer, 3 convolution layer, and 4 dense layer, with the increase in the convolution layer from 3 to 4, there is almost the processing time remains same. And again for 3 convolution layer, 4 dense layer, 4 convolution layer, and 4 dense layer model, we see that for all the types of kernel size, with the increase in the number of convolution layers from 3 to 4, the processing time increased. So finally, we implemented our based model for quality detection and noise classification and Raspberry Pi, and we see that we found that the method demonstrated a processing time of 71.62 millisecond, which is quite less than the segment duration of 5 seconds. And also presents the feasibility of the model on a resource constant and limited computing capacity platform. In table 5, we compare the existing models for ECG quality detection and noise classification of the Fusionet Challenge 2011 database. Most of the cases, the processing time shown in the last column is not computed, the model and the method in 8 have presented the model size, while our method has improved the model size by 85.89%. And in this same model, like in method 8, reference 8, we see that the accuracy of the model has decreased from 97.31 to 92.84 with the change in the computing platform from resourceful to resource constant platform. But while in our case, in both the resourceful and resource constant platform, we have seen no change in the performance of accuracy. Finally, we conclude that our CNN model is trained with two standard benchmark databases, the MIT Page Arrhythmia and PTP database, and it is tested with unseen FusionNet Challenge 2011 database, and the testing accuracy is 94.84% for quality detection of ECG signal and noise classification. The sensitivity for most of the noisy segments is 98.48%, and this significant model can significantly reduce the false alarm rate and is implementable on limited computing capacity platform, and with the processing time of 71.62 millisecond on Raspberry Pi computing platform. In future work, the energy consumption of the method can be evaluated for quality detection and noise classification on resource constant platforms. So we acknowledge ICMR for funding our project, and here are the references. Thank you.